Okay, so what do we have here? It's a problem 57, right? Ah, yeah, I wrote it down. 2657. And so what do we have here? Simple circuit, reasonably simple. Battery with a potential difference 9 volts. And we have 3 capacitors. C1, 4 microfarads, C2, 12, C3, 2 microfarads. Micro 10 to the power of -6, right? As I told you, 1 farad, capacitance of 1 farad is gigantic. Not usually, the Earth has a capacitance of a few farads, right? And the question is, we need to analyze this circuit. Again, what does it mean, analyzing a circuit full of capacitors? You need to know 3 parameters, 3 quantities of each of these capacitors. C, Q, delta V. C's are given, so we don't need to find C. So as a result, left only what? Potential difference, right? Across each of these capacitors, delta V's 1, 2, 3, and charge across each of these, and charge inside of each of these capacitors. Again, Q1, Q2, Q3. So once you know all these 6 parameters, you can say that you know everything about this circuit. Okay, so now let's start. So arrange your page in this way. So I'm going to draw several circuits here in the middle. And you see, I left on purpose some space above because I'm going to write something above, and then we're going to write something below. But most stuff will be below. Right? And that's one of the pieces which I like in this book, the way he solves problems like this. It's a very well structured. Everything is connected logically, right, based on the results which we got in the previous 2 slides. Right? It's all based on those results. Okay, so first we need to, you remember the goal of, the idea of an equivalent method of an equivalent capacitance. You need to replace these capacitors, in this case 3 capacitors, with a single equivalent capacitor. So our final circuit will be the simplest possible, battery across equivalent capacitor. But let's get that. Let's simplify the circuit to the simplest possible. So look at this and tell which capacitors are connected either in series or in parallel. Usually no troubles with that. Everyone sees that C1 and C2 are connected in parallel. Because again, you remember what's the test? To convince yourself that elements are connected in parallel. Potential differences must be the same. It doesn't matter what happens with the rest of the circuit. If potential differences stays the same, then we can tell that those elements are in parallel. And of course, in this case, potential difference will be the same. Because you see upper points, they belong to the same big piece of a conductor, right? So of course, all these points are going to be at the same potential. Let's say, 5 volts. Then points below, again, they belong to the same solid piece of a conductor, right? Again, they must be at the same potential. So let's say here 5 volts, here 3 volts. So 5 minus 3, you'll get 2 volts and 2 volts. And that will be true all the time. It doesn't matter what you do with the rest of the circuit. Potential differences are going to be the same. Okay, so now I can circle like this, and I can write that these are in parallel, connected in parallel, right? So now we can replace this circuit, these capacitors, two capacitors, with single first equivalent capacitor. So first I'm going to redraw this circuit. Okay, now I'm going to do by hand. So battery must work still in exactly the same way. Exactly the same delta V must be here, right? And now I can redraw this circuit. So this will be my first equivalent capacitor, which I'm going to label it as C12. And it makes sense, since we replace capacitor C1 and C2, so an equivalent capacitor is C12. Again, it's instead of these 2 capacitors. We're not touching this yet, right? So C3 is still here. So this is C3. And as I said, the battery still works in exactly the same way. So it means that still exactly the same delta V. And if charge Q is taken from this battery, exactly the same charge Q must be taken from that battery. So that's how we develop this method. So now let's find the value of this C12. So I can write, let me use blue above. Right, so we can find C12. Capacitors are connected in parallel, so we need to add their capacitances in order to find capacitance of C12. So it will be C1 plus C2. C1 is 4 plus 12, 4 microfarads plus 12 microfarads. So C12 equals to 16 microfarads. Okay, you know what? Let me frame it a little bit, because at some point I will need to find it and I will have to use it. So it will be easier to spot it. Okay, so we've made the first step. But again, it's not the last one, because you remember at the end we must have only one equivalent capacitor, one capacitor. But here we still have two. But we can replace them easily, because these two guys are connected obviously in series, right? Again, so far, usually have no trouble seeing elements connected in series or in parallel, at least in this case. And so I can draw the final circuit. So again, battery still works in exactly the same way. So exactly the same delta V. But now we have only one capacitor, which of course I'm going to call C equivalent. Right? And we can find the value that C equivalent, because guys are connected in series, and in the previous slide we derived the formula. So we need to add the reciprocals. Right? Again, and this is my least favorite formula. I don't like dealing with those reciprocals. All right. Anyway, so let me separate. So now we're going to deal with this capacitor. So 1 over C equivalent equals to 1 over C 1, 2 plus 1 over C3. And so now you can plug numbers or calculate. I usually write, bring to the common denominator, then flip it. I usually write the formula writing like this. C12 times C3 divided by the sum. So if you plug numbers, I will look at my notes, and the answer will be 16 over 9 microfarad. So this times, it will be 32 and divided by 18. Yeah, 16 over 9. 16 over 9 microfarads. Okay, so that's the value of the equivalent capacitance. Now, at this point, what can we calculate? We can calculate we can get a very important piece of information. Look, what is given about this C equivalent? We know its value. We know that potential difference across this capacitor is 9 volts, because again, when we do all this replacement, battery works in exactly the same way. So the same 9 volts now is across this C equivalent. So if you know capacitance and if you know delta V, you can find the charge in this capacitor. Right? Okay, you know what? Usually I like writing the definition of capacitance somewhere in the corner, because from this point we're going to use that formula a lot. And to reduce chances of making mistakes, because we will have to rewrite it in this form, in that form, right? So I prefer to write it somewhere in the corner. Let me do it here in red. So C equals Q divided by delta V, because from now on we will need this formula a lot. Right. So now we needed to find the total charge taken from the battery, and that will be the charge in the equivalent capacitor. So we need to get charge. It will be C times delta V. C equivalent times delta V, which is 9 volts. So now we can find the total charge. Now let me write it down. Where can I write it? You know what? I feel like invading that part of the whiteboard. Let me invade it slightly. At least I want to write a little bit, and then I will erase it. So I can write, so now we can find the total charge taking from the battery. And of course, that will be again from the formula, Q, which way I label it? Just Q. Okay. So it will be C equivalent times delta V. C equivalent 16 over 9. The value of delta V, 9. So it will be 16 microcoulombs. Right? So it will be equal to 16 microcoulombs. Correct? Yeah, 16 microcoulombs. Okay, it's a very important I don't know, piece of information. Pretty much the whole goal of this process of reduction of getting this simple circuit is to get the total charge. Now, once we get the total charge, it's sort of like getting at least something about this circuit. It's sort of like making a crack in the wall. Right? Once you made the crack in the wall, then it's easier to expand it, to make it bigger and bigger, to see the truth and the whole truth and nothing but the truth, right? So it's a very important. So now I can draw, yeah, so basically this charge, it's over here, the total charge taken from the battery. Again, I can draw it here because again, when you do all this replacement, battery works in exactly the same way, the same delta V, the same Q, and I can draw it even here. It's the total charge taken from the battery. You see, if I asked you from the very beginning, guys, can you tell me what's the total charge taken from the battery? I doubt that you will be able or would be able to answer it unless you have lots of experience of dealing with these problems and you can do the steps quickly in your head. Otherwise, no, it's too complicated to get the total charge immediately. But once you reduce this complicated circuit to the simplest circuit possible, then now getting this total charge is a piece of cake. Right? So now we managed to get that something, and now using this piece of information, we should be able to find all that. We should be able to reveal the whole truth. So now we need to start moving back. Here we use these formulas, right? So this formula and that formula to simplify the circuit. And now we are going to use those pieces of physics which I mentioned in the previous slides about charges, about the potential differences. Now we're going to use those bridges to move back, revealing the hidden values, hidden treasures, right? Okay, so what? How can we do that? So let's move back. First, this capacitor replaced these two capacitors connected in series. Which parameter is exactly the same for the equivalent capacitor and capacitors connected in series? That's what we discussed just 5 minutes ago in the previous slide, right? Which parameter? Which quantity? Charge. Charge is exactly the same. All right, you can look at the slides, right, or your notes. Charge is exactly the same. So it means charge in the equivalent capacitor equals to the charges in this capacitor and that capacitor. And we know the charge in the equivalent capacitor, it's a total charge. So that's the bridge which will allow us to move back from this circuit to that circuit, revealing some important pieces of information. So let me write this bridge so that Q equals to Q12 equals to Q3, and I can write that it's equal to 16 microcoulombs. So that's the bridge which allows us to move from here to there. And now let's see what we can get once we have this bridge. Look at what we know about C3 now. We know its value given 2 microfarads. Then now we have the charge in that capacitor. So can we find the potential difference across capacitor C3? Piece of cake now. Again, we need to use this formula. That's why I ask you, I told you, let's write it somewhere in the corner, because now we're going to use that formula a lot. Solving it for Q, for delta V, right, or for something else. So now we should be able to find potential difference across capacitor C3. And once we find that delta V3, we will have everything, we will know everything about capacitor C3. We know its value, we know its charge we just found, and we're ready to find potential difference. We will finish analyzing C3. Okay, so now let me write that down. So C3, so we need to find potential difference. So it will be Q divided by C. So let me write, so delta V3, it will be equal to, again, Q3 divided by C sub 3. And again, the value of Q3 comes from the bridge. So let me write numbers. So it will be 16 microcoulombs the charge, C3 2 microfarads, so we're getting 8 volts. So that's the potential difference voltage drop across this capacitor C3. So now, again, as I said, capacitance was given, we found charge, and now we know the potential difference. We finished analyzing capacitor C3. But of course, we still have C1 and C2, so the problem is not over. But some information we already found. Right. Okay, but again, we haven't exhausted this bridge. We still can find information about C1, 2. Again, C1, 2, we know its value, we found it, and we know the charge. Again, the charge comes from the bridge, so it means that we should be able to find potential difference across capacitor C1, 2. But even without using this formula, you should be able to tell me what will be the voltage drop across capacitor C1, 2. It's very simple, right? Because the total voltage drop is 9 volts across the whole circuit. We found that voltage drop across this is 8 volts. So it means that here only 1 volt left. So 8 plus 1, you will get 9. But anyway, I still want to use the definition of capacitance in order to find that potential difference. Okay, let me do it. So now I can write, so delta V12 equals to Q12 divided by C12. And again, the value of charge comes from the bridge. Let me show it this way with the green line. All right. Okay. So Q12, and that's, no, Q12, it's in the bridge, 16 microcoulombs, and divided by C12, 16 microfarads. That's why I circle it, because I knew at some point I would need it. So 16 microfarads, so 1 volt, as we knew from the very beginning analyzing voltage drops, right? Okay, so we exhausted this bridge number 1. So we revealed the whole, everything that possible. So now we need to, okay, let me separate it like this. So now we need to build the second bridge, which will lead us from this circuit to this circuit. And okay, using that bridge, we should be able to reveal the whole truth. So the last bridge. Inside of C12, we have information about this capacitor. So this is an equivalent capacitor instead of these two, right? And these replaced capacitors connected in parallel. Which quantity, which parameter is exactly the same for a capacitor, for an equivalent capacitor and capacitors connected in parallel. That's the slide which we discussed at the end of previous class yesterday, when we analyzed capacitors connected in parallel. And which parameter is the same? Potential difference. Potential difference across an equivalent capacitor must be equal, and we justified, we proved it. must be equal to the potential differences across capacitors connected in parallel. So that's that piece of physics we need to use now, and I call it like a bridge number 2, which we use to move from that circuit to this circuit. So let me write that bridge again in red because it's a important. So potential difference delta V12. Okay, I'm trying to estimate the amount of space. So delta V12, right? Potential difference across this capacitor equals to delta V across the first capacitor equals to delta V across the second capacitor. And so what's the value? Delta V12, it's from here. We found it. In the previous step, you see everything is so nicely linked. That's why I like how the author structured this problem. So delta V12, it comes from here. Right. So now let me write that down. So it's a 1 volt. And now, what can we find? We know voltage drop across capacitor C2. We also know the value of capacitance to 12 microfarad. So if we know potential difference and capacitance, we should be able to find charge. Again, you see, we use this formula all the time. So now we need to solve it for charge. It will be C times delta V. All right, so it will be Q. Okay, we are discussing Q2. I mean C2. All right, so it will be Q2 equals to C sub 2 times delta V sub 2. And the value of potential difference comes from the bridge. Here we were getting charges from the bridge. Now we're getting potential differences from the bridge. So delta V2 comes from here, and C2 is given initially. What's given on is given initially. So it's a 12 microfarads times delta V. It's 1 volt. Okay, I will write underneath. So it's a 12 microcoulombs. So that's the amount of charge stored in the second capacitor. Okay, so now look, now we finished analyzing capacitor C2 because we know its value. Then we know the voltage drop across that capacitor, and now we know it's the charge in that capacitor. Done with C2, but still we have C1. And of course, finding the charge in the C1 will be done in exactly the same way. So we know the potential difference, we know the value of capacitance, and again, using this formula, so charge will be equal C times delta V, C1 times delta V1. Okay, so, and that is basically the last step. Q1 will be equal to C1. Okay, let me finish this problem with just a half a minute left, and we'll have a break. C1 times delta V1, right? C1 is 4 microfarads times delta V1 comes from the bridge. Let me show it again. So, and times 1 volt. So the answer is 4 microcoulombs. So now I can write done, put a big happy face, and that's the problem. Yeah, as I said, I like it. I like the structure of this problem, right? It's in my opinion, it's very well done because everything is so nicely connected, right? If you basically remember those formulas which you can use to find equivalent capacitances, and then realizing the physics, these pieces of physics, remember this piece of physics, everything can be found easily. Right? It takes some time to get through, and usually, I don't know, maybe like 99% of students have no troubles at all finding this C equivalent, getting to this point. Except for occasionally students, as I said, forget they find this 1 over c, and then they use that number as c equivalent. No, you need to also flip that. So that's the only place where they make these silly mistakes. But lots of troubles in this second part. It's usually students start writing something which doesn't make much sense, right? Usually at least 30% of students make lots of mess in this part. Although again, it's all based on information which we discussed in the slides, and now you just need to use them properly, and then the rest, it's all application of this formula. Okay, anyway, when we get to the equivalent resistance, steps and problems like this will be very similar. Right, but of course we will have to adjust some formulas, but the idea will be very similar, and I will solve the problem in a very similar way.